Lesson 99. We will continue to look at normal distribution in this lesson. So first, let's recall the notation for normal distribution of a random variable x is defined by the mean and the variance of the distribution in this notation outlined in the box. We also know that the PDF of a normal distribution function relies on both sigma, the standard deviation, as well as the mean, okay, which gives us the profile of the bell curve. You have also learned in the last lesson how to use your calculator to calculate probability under the curve for regions that are either less than an x value, greater than an x value, or between two x values. You can also find, using inverse normal, the z-score of a standard normal distribution. So in this lesson, we will just do a couple more examples so that you're aware of how the normal distribution can be applied in real life situations, and also perhaps looking at its relationship or how we can combine different types of probability distributions in problem solving. Okay? So here is example 1. Given that x belongs to a normal distribution with a mean of 3 and a variance of 16, determine p of x greater than 5. So the key in this question is to notice how 16, given to you in the question, represents the variance. As such, the standard deviation is actually just 4. Okay? When I calculate p of x greater than 5, I will be using normal CDF. On a calculator, I'm looking at greater than, so starting from 5 as a lower bound to a really large number, 1000 should do. And then you type in the mean, you type in the standard deviation of 4. And this works out to 0.309 if you round it to 3 significant figures. Okay. B, I'm looking for p of x greater than 5 and x is greater than 8. Okay. So if I make a sketch of this situation here, so here's a bell curve. The middle is 3. I need something bigger than 5 and intersecting with something greater than 8. Of course, this is not drawn to scale. So the area that's greater than 5 is here in green. The area that is greater than 8 is over here. So essentially, what we are really looking for is p of x greater than 8. Okay? So using your graphing calculator, you should get 0.106. Part C. Now we are interested in finding the probability of x greater than 8 given that x is greater than 5. So we are revisiting conditional probability. Recall that conditional probability is calculated by dividing the end of the two events we are mentioning over the probability of now your restricted sample space or your condition, in this case x greater than 5. Okay. So we have found these components in parts A and B. So let's substitute these numbers. You can keep the original numbers on your calculator to maintain accuracy. And 0.343 would be my final answer. Okay? Here is example 2. On a cherry farm in the Niagara region, 5% of the cherries weigh more than 8.5 grams and 7% weigh less than 5.1 grams. The masses m of cherries are assumed to be normally distributed. Determine the expected value and variance of the masses. So we're working backwards now because we're so used to having the mean and the variance given to us. But this time, is not, right? We just know certain facts about this bell curve itself. So we're going to have M to represent the masses of these cherries in grams. I'm a visual person. I find that it is always helpful if I turn the descriptions of the probabilities into a diagram. So first, 5% weigh more than 8.5 grams. So it's very little. 5% is very little. So when I fill out this diagram, I know that it's going to be a small region, the top 5%, with a cutoff of 8.5 grams, okay? And then the second statement, it tells us that 7% weigh less than 5.1 grams. So the bottom 7%, so let's say somewhere here, okay, has a higher cutoff, the upper bound, as 5.1 grams, okay? Like that. So I don't know much about it except for the fact that P of M greater than or equal to 8.5 is equal to 0.05, and also P of M less than or equal to 5.1. And yeah, I don't really need the less than, but here it doesn't really matter, equals to 0.07 because it's a continuous variable, okay? Well, without the mean and standard deviation, we have to rely on the standard normal distribution, which is z-score. So to find the first z-score, I'll put a note here. You don't really have to write down like what exactly you entered in your calculator. So I'm going to put it in a different color instead, okay? But theoretically, we're doing an inverse normal of the percentage of 95%, okay? It's the lower half that we're dealing with. And this gives us the first z-score as 1.64, okay? With the z-score and the actual data point of 8.5 grams, I can at least substitute that into the z-score formula. If I rearrange this to isolate for mu, I have 8.5 minus 1.64 sigma, okay? Let's see. So on the right side, I guess the only thing that we can really do is the same thing as what we have done here. So let's look up Z2 using inverse normal. So again, you don't have to write this out. 0.07 in this case, okay? And so Z2 turns out to be negative 1.48. And this makes sense because we're to the left side of the mean. So you get a negative z-score. The weight here is 5.1 minus mu divided by sigma. Arranging, I have 5.1 plus 1.48 sigma. So it seems like we do have a possible solution because we have two equations with two unknowns. I'm going to set equation 1 equal to equation 2. And this gives me 8.5 minus 1.64 sigma equals 5.1 plus 1.48 sigma. Solving the equation, I get 1.09 for sigma, okay? And we're looking for the variance as such. Sigma squared would be square of this number, which is 1.19 if I round it to 3 significant figures. Now we have to find a mean. Sub sigma equals 1.09 into one of the equations. I'm going to choose equation 1. It works out to 6.7, rounded to 3 sig figs. Okay, so the expected value, which is the mean, okay, of the masses is 6.71 grams. Okay, and then the variance is 1.19 grams. Okay. Here is question 3. The heights of a group of 3-year-old children are normally distributed with a mean of 88 centimeters and a standard deviation of 7.3 centimeters. 8. Determine the probability that a randomly selected child is taller than 100 centimeters. So I'm going to start by writing down a let statement. Let x centimeters be the height of 3-year-old children. Okay. And so here we have x belongs to a normal distribution with a mean of 88 and a standard deviation of 7.3, but I have to square that as the variance. So here we're looking for p of x that is greater than 100. Okay. Using my calculator, we're thinking about the normal CDF function with 100 as a starting point, a really big number as the end point, mean, and SD like that. If you need a hint, it works out to 0.0501. So roughly 5%. Okay, so it's a small fraction of the population. B, in a group of 50 children, how many are expected to be taller than 100 centimeters? So now let's analyze this, right? We are told a group size, which is not what, we usually see in a normal distribution. And the question here is how many are expected to be taller than? So we are dividing the children into two groups. The groups that are taller than 100 centimeters and the group that are not taller than 100 centimeters. Does it sound familiar? Are we still talking about a continuous variable here? How many children? No, that's discrete, right? So here we have this discrete random variable that deals with a set size, which is 50 children, with two outcomes, and the outcomes and the events are independent, because if one child is taller than 100 centimeters, it doesn't affect whether the next child I pick from the group is taller or shorter than 100 centimeters, right? So here, instead of thinking about a normal distribution, we are going back to binomial probability distribution. So let y be the number of children taller than 100 cm. Okay, and y belongs to a binomial with sample size of 50, and the probability of success would be the probability of children taller than 100 centimeters, which is what we found in part A. And this style of a question, of a multi-part question, is very, very popular or common on IB exams, okay? So here we're looking for the expected value of y, which is for binomial n times p, sample size 50, probability of success, which works out to 2.5, okay? And it is okay to have a decimal number. Remember, this is a theoretical average. Part C. In this group of 50 children, find the probability that at least 15 of them are taller than 100 centimeters. Okay, so let's organize our thoughts here. Now we know that we're talking about a binomial model, which is a discrete model. Counting is important. Okay, so at least 15. So I guess I'll put 15 here on the number line, 16, 17. I have 14, 13 over here, and so on both sides. Okay, at least 15 of them. Do we include 15? Yes, we do. And all the way up to child number 50. How many cases do we have to add together? Too many, okay? Well, if there are too many cases to be added together, what's our other choice? The other choice, of course, is to remove the irrelevant ones. Okay? Because we can now activate another command on your graphing calculator that you have used before, binomial CD for the cumulative up to, the 14th case. So include 14, but do not include 15. So here, your n, number of trials, is 50. Probability of success, 0.0501. And then up to trial number 14. Okay, so that's what you should be doing. And let's write this out as a solution. I'll use the space below. P of y that is greater than or equal to 15 is equal to 1 minus p of y open less than 15, or to be exact, I like using this notation myself because it reminds me of the fact that I have to include case number 14. So let me take in my calculator, go to binom CDF, is B on my menu, 50 trials, 0.0501, x value is 4, paste. This is 1 minus 0.9999, like lots of it, okay? So 1 minus that gives me 1.32 times 10 to the negative 8, which is a very unlikely situation, okay?